Hi everyone and welcome to a new video about noise analysis in op-amp circuits. This is our example number 10. In this example we will look at the two-stage amplifier with the RC filter. So that will be our example number 10. And again we will look at the calculations and also verify these calculations using SPICE simulations. So let's look at the example. We have the following circuit given. What you have is an inverting amplifier, in this case with a capacitor as a feedback capacitor, and we have in cascade a non-inverting amplifier. We see in this case the voltage which is applied to the input resistance of this inverting amplifier, but in addition we have R3 which is connected to the non-inverting input of the first stage, so that will be also has some effect on the performance in noise. Now we have 5 resistors, R1, R2, R3 and R4 and R5, and we have 2 op-amps OPA 209. The values are shown here for the resistors, and the capacitor has a value of 200 nanofarads. So as we did in the previous examples, we will look at the input referred RMS noise voltage, we will calculate that, and also the output referred RMS noise voltage for this circuit. So let's look at the example solutions, and first we start with the op-amp specifications as we did in the previous examples. Now from the datasheet of the OPA 209 you will find this plot which will give you in graphical form the input noise voltage spectral density and also the input noise current spectral density. These are really important plots from the datasheet. You also see a table which is shown here as a small portion of it, which give you the very important parameters of the op-amp and some test conditions to determine the parameters. Now what you see here, for example, is the DC open loop voltage gain, which is given by this symbol. It has a value of 132 dBs. And you can see that in the table here, which is the open loop voltage gain. The gain bandwidth product is in this case 18 megahertz for this op-amp. You can see that here in this frequency response part. This is a very important parameter for our noise analysis. The broadband noise voltage spectral density is given by this sample. It has a value of 2.20 nanovolts per root hertz. That is shown here with this value or units, and you can see the condition for the value of this input noise voltage spectral density in broadband region. You can also see that in the graph, which is actually the part which is frequency independent, which is a flat part of the graph. Now you have also the similar for the input noise current spectral density, but in the broadband region, given by this sample. It has a value of 500 femtoamps per root hertz. That is shown here. This is the unit. These are the units. You can see the test condition again, but you can also see that from the graph of the input noise current spectral density. This part is 0.5 picoamps per root hertz. It stays constant independent of frequency, and 0.5 is of course 0.5 picoamps is of course equal to 500 femtoamps. Now we have also the first region. This is called the 1 over f region, which is frequency dependent. 1 over f noise voltage density in this part, and for specific frequency we select the value, in this case for 0.1 hertz. This is simple for that one, and that will be 20 nanovolts per root hertz. That's actually shown here. And in a symbol form we will do that also for the 1 over f noise current density, and we will look at 0.1 hertz in that region, and that will be 3.75 picoamps per root hertz. Actually you can take any frequency here which you prefer. You can also take 1 hertz, but you need to of course stay in that 1 over f noise region, also for the current and also for the noise voltage, and also the current noise. Okay, those are the very important parameters. We will use this later on in our calculations. So let's next look at the circuit performance. We have of course the gain. We have the closed loop signal gain, which will amplify the signal, and we have also the closed loop noise gain, which will amplify the noise specifically. In addition, we have the performance and the frequency, which is then the bandwidth. We have of course the closed loop signal bandwidth. We have also the closed loop noise bandwidth, and this is a very important parameter we will use in our noise analysis. Now for the first stage, just considering only the first stage, we can see that the signal gain is of course in a DC portion just the formula for our inverting amplifier, which is just minus R2 over R1, which is then minus 22 kilo ohms over 1000. That will give you minus 22. The noise gain is always defined looking from the non-inverting input, and this resistor R3 will not have effect on that source here. That will be then the formula for the non-inverting amplifier, because this is disabled and you look at the DC form, this is open, so you will see 1 plus the feedback divided by the R1. That's shown here, and you will have 23. So in absolute sense, the noise gain is a little bit larger than the signal gain. The signal bandwidth for the first stage we will calculate using the gain bandwidth product divided by the noise gain of that first stage. Now we have for the op-amp 18 megahertz for this OPA 209, and the noise gain is just calculated as 23. Now if you do the math, you will get 783 kilohertz. That is just considering only the first stage, but we need to of course also consider other part of the circuit. We have our RC circuit in feedback that will create also a pole frequency, and that pole frequency for this portion is determined by the capacitor C and the resistor R2. So that will be done 1 over 2 pi R2C. Now given the values here, so 200 nanofarads and also 22 kilo ohms, I just substitute the values for R2 and the C. I get 36.2 hertz, which is very small compared to that one. That will be discussed in the next discussion. Now, if you just look at the second stage only here, that will give you the signal gain, looking of course as a non-inverting amplifier, because you inject the signal here for this stage. That will be 1 plus R5 over R4. That will give you the value of 11. That will be the signal gain for the second stage. Noise gauge will be exactly the same, because this is the source where you place, this is the place where you place the noise voltage source. Again, that will be also 11. Now, specifically just looking at the second stage, that will be then again the signal bandwidth for the second stage will be the gain bandwidth product over the noise gain. Now, if you do the math here, again similar to the first stage, you will get 1.64 megahertz. So this signal bandwidth is much larger than the first stage. Of course, since this is a cascade, so we have the first stage in cascade with the second stage, and also we have that RC feedback filter, we need to of course consider that in one total, as a one total circuit. So we see that pole frequency P1 is much smaller than the signal bandwidth 1. And also the pole frequency 1, we also see that it is much smaller than the signal bandwidth 2. Now, since these are, of course, two stages are in cascade, the closed signal bandwidth of the second stage will be limited by the pole frequency P1 of the RC low-pass filter of the first stage. So that means actually the complete signal bandwidth, and also in addition to the going to the noise bandwidth, will be determined by this RC low-pass filter. So then we can assume it is just a first-order circuit or first-order system. Now, looking from the noise perspective, we need to of course have a brick wall conversion factor going from the signal gain to the noise gain, and that factor is for the first-order system pi over 2. Now, so the noise bandwidth will be then the Kn, which is then the conversion factor going from the signal bandwidth to the noise bandwidth, will be then a Kn times the pole frequency P1. Now, if you do the calculations, you will get pi over 2 times that frequency. That will give you 56.9 hertz, almost 57 hertz, which is very small. So we will see what kind of effect this will have on our performance. Okay, the next one is the total noise. Of course, we'll look at the total noise in separate stages. Noise of the first stage, will be multiplied by the noise gain of this first stage, but will be multiplied by the signal gain of the second stage. So this gain or this stage will be seen as a noise-free stage. The noise of the second stage, so actually noise at this input of the second stage, will be multiplied by its own noise gain. So that is of course important to notice. So this will be very important in our calculations. That means actually for the first stage the following in mathematical form: the output referred RMS noise voltage at this node, all the way to the output, due to that first stage will be the noise gain of the first stage times the signal gain of the second stage times the input referred RMS noise voltage due to that first stage only. So in this case you can see noise gain of the first stage, but the signal gain of the second stage, because the second stage is assumed to be noise free. So that is actually due to that superposition. Okay, now looking only to the second stage, we can say the output referred RMS noise voltage due to that second stage only is that noise gain of that second stage times the input referred RMS noise voltage of that second stage only. So that's actually the expression. Now we will of course need to add them up to get the actual total output referred RMS noise voltage. So in general, we can say the following for all circuit which is in cascade. So if you have a multiple stage amplifiers, noise source will be multiplied by the noise gain of the stage it is connected to, but it will be the following for noise source will be multiplied by the signal gain of the subsequent stages. So if you have a noise source here, that will be multiplied by the noise gain of this stage, but it will be multiplied by the signal gain of the next stage, considering of course a superposition principle. So if I now move from the actual circuit to the model of the circuit using the noise current source and noise voltage source of the op-amp, also doing that for the second stage, you will get this circuit. So using superposition, the calculations are then carried out as follows. Calculate the output noise voltage of the first stage, considering the second stage again noise free, so it is an ideal amplifier. The next one is the calculate the output noise voltage for the second stage only. That's actually just considering the second op-amp. And then combine the result using root sum of squares. Now that will be then calculated using this formula. This is the part for the first stage due to that first stage, and this is the part due to that second stage, and this is a total, subtotal. Okay, now we have some notes, very important. Noise from the first stage can be slightly reduced by the bandwidth limits of the second stage, because this part of the circuit will create a pole. This part of the circuit will also create a pole, actually two poles, because op-amp on its own has its own pole, but also the RC filter. But when you combine those three poles or that complete circuit together, you will have some pole shifting, and that degree of shifting will of course also shift your bandwidth, actual bandwidth of your circuit slightly. That really depends on the location of the poles. Now, if you have a slightly reduction of your bandwidth of the total circuit, that will of course also reduce your noise bandwidth, and that will also reduce your total output noise voltage. So it might be the case that what you have calculated is a little bit larger than what you have simulated and also what you have measured. In addition, we will use a rule of thumb when several op-amps are in cascade like this. We have two stages. Noise bandwidth is actually approximately equal to the lowest noise bandwidth. That is most of the time the case. However, some of the higher bandwidth amplifiers can still roll off some noise, so that will be of course very important to consider. So this is just a rule of thumb. In most cases this is valid. Okay, now let's look at the first stage only and then calculate the noise performance. Looking of course at the first stage only, we know the input referred RMS noise voltage has three parts, which is of course the noise due to that input noise voltage of the op-amp. That is also the noise due to that input noise current source of the op-amp, and also due to the resistors in that first stage. That will be of course a thermal noise. Now those combined, these three will be combined again using root sum of squares, and you get the total result in this formula. Now first one, the input referred RMS noise voltage due to the internal op-amp noise voltage, this one. Now, that is on its own also composed of two parts, because we have seen the plot in the datasheet, which has a 1/f noise part and also the broadband part. So the broadband noise and also the 1/f noise. Now, we know we can calculate also these two using exact same procedure, using root sum of squares. So if you have this and also this in RMS, you will calculate the total effect, so the input referred RMS noise voltage due to that source only, using this formula. Now let's look at the broadband noise voltage. For that, of course, we need the op-amp specification. This is the input referred RMS, input referred noise voltage spectral density, shown here specifically for the first stage. Exact same, of course, because we use the same op-amp. This is then 2.20 nanovolts per root hertz. Noise bandwidth was 56.9 hertz, because that is due to that RC low pass filter, which is in this case the limiting factor. If you do the math, you will get 16.58 nanovolts RMS. Now for the 1/f noise part, it can be calculated using this formula. In this case, the FH1, F sub H1 is actually the closed loop noise bandwidth. So that's in this case again 56.9 hertz. F sub L1 is a selected frequency to calculate the normalized 1/f noise voltage, and that will also use in this formula. So in most cases it is taken as 0.1 hertz, which is also shown here in the specifications. So if I move on, then calculate the normalized noise voltage, this one, that will be calculated using this formula. That will give me, if I do the math, 6.325 nanovolts RMS. Then I will substitute this in here, also the noise bandwidth due to that RC, low pass filter and the feedback, and also the selected frequency. And I will get 15.93 nanovolts RMS. Now I will combine these two values in this formula, and I will get the total effective value due to that internal op-amp noise voltage of the first stage. That will give me the following result. You can see it is approximately 23 nanovolts RMS. That's for the first stage, only considering this noise source. The next one is the noise current source for the input stage, and then looking at the input. This will be calculated using the equivalent resistance seen by the source and also the noise current source in RMS value. So this is actually I sub N1 and also the equivalent resistance. So that will be, of course, using this one. We calculated the voltage using Ohm's law, because we can then do current times that equivalent resistance. But that noise current source of the first stage at the input, it's on its own also composed of two parts, because we have seen in the datasheet it has the 1/f noise and also the broadband part. So we also have that. Again, that can be calculated using this formula, root sum of squares. The broadband part, very similar to the noise voltage analysis. Again, this is from the datasheet, it's shown here. This is the noise bandwidth, which is of course due to that pole frequency by the RC circuit and a feedback. Now, if I do the math here, you will get 3.77 picoamps RMS. Now, 1/f noise current, also very similar formula. Again, we calculate this one from selected frequency, and also this is the noise bandwidth. So again, from the values, again, we take the 0.1 hertz, we just use this, and then calculate first the 1/f noise normalized noise current. That will be, of course, used here. And if I now substitute all the necessary values, I will get approximately 3 picoamps. It will be 2.99 picoamps RMS. Now, combining these two using this formula, I have now this expression, and then I have 4.81 picoamps RMS. Of course, we need to go from the current noise to the voltage noise. So we need to calculate also the equivalent resistance. That's actually the first part is due to that R1 and R2 in parallel, looking at this node. So the parallel combination will be approximately 957 ohms. But in addition, this current source will also see that R3. So that is also another resistor we need to take into account. So using Ohm's law, this will be then the following. So we have then the input referred RMS noise voltage due to that noise current source, and also the resistors R1, R2 and R3 in this form. So this is the first part. You just calculate this, square that, and you also calculate that one, do that R3, square that, and you will take the square root of that of the summation. Now the result is the following. It will have 4.60 nanovolts RMS. That will be the value for the first stage, considering only the source and also the resistor around it. Okay, the next step, the final one for the first stage, is the contribution due to that resistors. We know that can be calculated using the thermal noise or white noise formula, which is given by this expression in general, and these are the parameters, the K of the Boltzmann constant, given by this value. T is the absolute temperature, in this case 300 kelvins at the room temperature. R is the equivalent resistance seen at the node, and also we have the noise bandwidth in hertz. Now for the first one, for this case, in this first stage, we have the first equivalent resistance and also the R3, and also the noise bandwidth of 56.9 hertz. So these are the necessary parameters to substitute that in this formula. Now the first one, only due to that equivalent resistance 1, you substitute the values, you will get very close to 30 nanovolts RMS. In a similar form, using this R3 only, you will get 9.70 nanovolts RMS. Now we need to, of course, determine the actual contribution of these three resistors in thermal noise voltage. Again, we use the root sum of squares and add them up. That will result in 31.5 nanovolts RMS. You can see this is actually the most dominant part in this part of the circuit. Okay, now we have the three parts for our first stage. Now we can calculate the total input referred RMS noise voltage due to that first stage. Again, using this formula, we know the noise contribution by this noise voltage sort of the op-amp was given by this value. For the noise current, the contribution of the noise current was this 4.60 nanovolts RMS, and the resistors gave us 31.5 nanovolts RMS. Combining these in this root sum of squares formula, you will get, just substitute the values, 38.1 nanovolts RMS. That is actually the effective value at the input. Now we need to, of course, calculate the contribution of all of these at the output using the closed-loop noise gain of the first stage, which is 23, and also the closed-loop signal gain of the second stage, because we consider the second stage as an ideal amplifier. That is 11 for the signal gain of the second stage. And we need, of course, the input RMS noise voltage of the first stage, which we have calculated now as 38.1 nanovolts RMS. Now we can calculate, of course, the output noise voltage in RMS due to the first stage, considering the second stage as an ideal amplifier, noise free. This is the formula: noise gain of the first stage, signal gain of the second stage, and also the input referred RMS noise voltage. If you substitute the values, you will have 23 times 11 times 38.1 nanovolts RMS, and that will give you now 9.63 microvolts RMS. So that will be the result. So this is what we have now, and that will be used later on in the total output noise voltage. Now the second stage, that goes in a very similar form. Again, we have the input referred RMS noise voltage of the second stage. It has also three parts, so I will go a little bit faster in this case, because we have also the internal op-amp noise voltage source, which is this one, also the noise current source, also the resistors. Each of them will contribute noise at the input in terms of RMS noise voltage. And that will be, of course, reflected in the output, and we will see what kind of effect it has on the total output noise voltage of the circuit. Again, using this formula, specifically for the second stage. Again, the input referred RMS noise voltage due to that source, noise voltage source. Again, this is composed of two parts, the broadband and the 1/2 noise part. This is the formula. We have seen also that for the first stage. again using root sum of squares. Now broadband part, and in this case, very important, since this is of course the second stage, but it is limited by the first stage RC low pass filter, noise bandwidth of the second stage is the noise bandwidth of the first stage, which is then the 56.9 Hertz, just due to that RC low pass filter. That's very important, so don't use the separate noise bandwidth formula or noise bandwidth value of the second stage. Now again, using the formula for the broadband part, you will substitute the value, will have 16.58 nanovolts RMS, just exactly the same as for the first stage. So I will go a little bit faster here. Also 1/f noise part, again exact same procedure, exact same values we need for the calculation, and that is for the normalized value. And if now also calculate the 1/f noise part, that will be 15.93 nanovolts RMS. Combining these two using this formula, you will have now the value of approximately again at 23 nanovolts RMS. Okay, that's for the first part. Now we go to the current source, again in a similar form. In this case, we also look at the equivalent resistance seen by the source and also the RMS value of that noise current source. In this case, the equivalent resistance is different because now this current source will see R4 and R5 in parallel. So, and again, we will use Ohm's law to calculate that input noise voltage, converting that input noise current from using the resistors. This is again composed of two parts, which is the broadband and also the 1/f noise current. Again, we will calculate that using the root sum of squares formula. Now, again, the broadband noise current, again, we consider very important only the noise bandwidth of the first stage, using it also for the second stage because it is in cascade. For the broadband part, we have this value, and for the 1/f noise part, we have the required elements, and we have then this value. So this is the 1/f noise current, and this is the broadband noise current for the second stage at the input. Okay, now we need to of course add them up using this formula to get the actual total input referred RMS noise current source value, which is then 4.81 picoamps RMS. Now we need to convert that using Ohm's law into the noise voltage source in RMS. So the equivalent resistance, again R5 and R4 and R5, these are 820 and 8200 in parallel, and you will do the math, you will get 746 ohms. If I now calculate this using Ohm's law, you will get the value of approximately 3.6 nanovolts RMS. That will be then the result just due to that noise current source and also the resistors. Now the final one is of course the contribution by the resistors R4 and R5. Again, we will use the formula for the thermal noise or the white noise. Again, this is your general formula, and these are the parameters we need to use in this formula. In this case, for this part of the circuit, we have of course that parallel combination of R4 and R5. We just calculate that, and also the noise bandwidth. Now using this formula, the value for the equivalent resistance and also the noise bandwidth, now for kT, and also the temperature, we have the resistor and also the noise bandwidth, we will get 26.48 nanovolts RMS. Okay. Now we have the necessary elements to calculate the input referred RMS noise voltage for the second stage only. That's again this one. We have this for the due to that noise voltage source of the op-amp. This is due to that noise current source of the op-amp and also these two resistors. And this is just the terminal noise voltage due to the resistors R4 and R5. We will combine that here using again root sum of squares. That will give you this expression. Just substitute these values in the right location and you will get 35.3 nanovolts RMS. Now from here you can calculate the total output referred RMS noise voltage for the second stage. We need for that the closed loop noise gain of the second stage, which is 11, looking from this part. And then of course the input RMS noise voltage of the second stage, we just calculated 35.3 nanovolts RMS. Now we can calculate that using the noise gain of the second stage and also the input revert RMS noise voltage of the second stage. Substituting the values, you will get 0.388 microvolts RMS or 388 nanovolts RMS. So this is the result for the second stage. Now we have the necessary elements from the second stage. We already have the output contribution in terms of noise voltage due to that first stage. Now we can actually look at the total effect. So the total output revert RMS noise voltage. That will be calculated again using the formula for root sum of squares, because this is the contribution of the first stage only at the output, and this is the contribution of the second stage only at the output. Now, substituting for the first stage, we had this one, and for the second stage, we have this one. You can see actually the first stage is much larger than the second stage. So that's actually the case most of the time when you have a high gain relative to the subsequent stages. In this case, the gain of this one, noise gain, is 23, and the noise gain of this one is 11, so this is larger than that one. So this will be dominant also in this part of the circuit. Now, if you want to combine this using this formula, add the values here, you will get 9.64 microwatt RMS, which is very close to the 9.63 microwatt RMS. So if you actually want to have a shortcut calculation and you see that the noise gain of the first stage is much larger than the second stage, you can just ignore actually the second stage for very general first order approximation. Okay, now let's make an observation. Again, the total output noise voltage of the total circuit is almost determined by the noise contribution due to the first stage only. This is a very important observation. We need to, of course, set some notes here. If the first stage is a high gain stage, that is of course mandatory compared to the subsequent stages, then this first stage will dominate the noise performance of the circuit. But that's only the case when this is high gain relative to the subsequent stages. Now, because the first stage or the input stage will dominate the noise performance of the complete circuit when it is a high gain, engineers will often use very more expensive low noise or ultra low noise amplifiers for the input stage, and then less expensive amplifiers for the next stages to keep the cost at the minimum. So this will be very nicely designed in low noise amplifier, but these subsequent stages will be just not that expensive. That's what we most of the time do when we design a low noise amplifier. Okay, that's for this part. Let's also look at the signal to noise ratio, SNR, in the next analysis. SNR is a measure that compares the desired level of your signal to the noise level. In a more precise way, it is actually a ratio of the signal power to the noise power, and expressed in decibels. If you have a ratio which is larger than 1 or greater than 0 dB, in case you have more signal than noise. But if you have a ratio which is between 0 and 1 or less than 0 dB, which is the negative, that in case you have more noise than signal, which is of course not what we want. So we need more signal than noise, so we will actually want to have a large value for SNR. Now, for this circuit, the SNR at the output for a specific frequency can be calculated using this formula. For that, we need the output revert RMS noise voltage in total. We already calculated that. It was 9.64 microvolts RMS. If I now substitute that in this formula, I will get approximately 100 dBs, 100.3 dBs. We will check it also in the simulations. Okay, that's for the SNR. Let's go to the simulations. First one, the frequency response, the signal gain, and also the bandwidth. That the signal gain or the DC gain is shown here. It is 47.7 dB approximately, and we can see the cutoff frequency also here. It is 36.17 Hertz, and we had actually in our calculations 36.2 Hertz, very close to what we actually have calculated. So that's actually a very nice result. And what you also see is the total DC gain here is this, which is also from the calculation exactly the same, because the signal gain of one first stage times the signal gain of the second stage, which will be then the 20 2 times 11 will give you this result. And the signal bandwidth, due to that first pole, we have calculated using the R2 and C, again shown here in great detail, all was calculated to be 36.2 Hertz. So that is a very nice result considering the cutoff frequency, also the DC gain of the circuit. Okay, so simulated very close to the calculated for the cutoff frequency, because that will also determine your noise bandwidth. Okay, then input noise voltage spectral density. You can see the following plot. It starts actually in a region where the input noise voltage spectral density is dependent on the frequency, and that part is now independent of frequency, and then it will go again up. So we have actually 3 regions: dependent part, which is the 1/f noise part, independent part, which is called the broadband noise part, and the part which is then approximately increasing after 200 Hertz. Now in our case, since our circuit of course has a filter cutoff frequency approximately at 36 Hertz, this frequency increase in noise will not have effect for our circuit. You can see that in more detail in the output noise voltage spectral density. It again has a 1/f noise part, frequency dependent, and a little bit of part which is almost frequency independent, still a little bit of dependency here, but it will go down all the way to 0 approximately if you go through higher frequencies. So again, that is due to that op-amp limitation, and also actually due to that R and the R2 and C. So at the output we don't have any problems with increasing noise at the input in the spectral density. Okay, now the integration bandwidth, which is a very important topic. We will first consider it also before we move on to the next analysis. At high frequencies, the feedback capacitor acts actually as a short circuit. So when the frequency goes to infinite values, but the noise gain is still unity. That's actually an interesting thing, because then you have a unity gain feedback here, but noise gain will not be 0. Signal gain will go to 0, but the noise gain will not be 0. So that means actually even if you have high frequencies, you still have noise at the output. So the noise voltage at the output will not be limited if you integrate the noise up to infinite frequencies. So the total output noise voltage increases without limit for all cases of the capacitor value. So it doesn't matter which capacitor you have here, it will just increase. Now technically we should always integrate to infinite frequency. That's actually what we should do in theory. But the key point what we were discussing here is the need to integrate beyond the cutoff frequency we have just calculated, which was 36 Hertz approximately, or the noise bandwidth in the SPICE simulations. So when you integrate using SPICE, it is not practical numerically to integrate up to infinity. That will give you very different results. However, it is also not necessary to do that, because the noise contribution a decade or so approximately after the cutoff frequency is not really significant anymore, because you have also filtered out a lot of noise. Impractical. So during the integration, the total noise should converge actually to the final value. That will include all noise before and after the cutoff frequency, or which is called the -3 dB bandwidth. So in summary, it must be stressed that the noise after the cutoff frequency limit needs to be included in the total noise. As a rule of thumb, we as engineers use the integrate at least 1 decade after the cutoff frequency. So if you have an expected result, you can integrate up to or approximately around that 1 decade after your cutoff frequency. That will be also a very accurate result. So using the rule of thumb given here, the frequency where we should determine the total output noise voltage for each capacitor value, but in this case we have just one capacitor value, will be then called the integration bandwidth. And that integration bandwidth is then 10 times, which is then 1 decade, times the signal bandwidth of the first stage, which is of course determined by our pole frequency. So that is actually the 36.17 Hertz or 36.2 Hertz. If you multiply by 10, you will get 361.7 Hertz. that is the frequency where we need to check our total output referred RMS noise voltage. So that is important to consider. If you have, of course, a situation where you have a feedback capacitor, which will be a short, and then of course noise gain will be still unity, and you will just integrate your noise without a limit. Okay, let's look at the total RMS noise voltage at the output, and we'll see what we actually mean by that integration bandwidth. Okay, we have calculated this one. That's actually our calculation. The total RMS output noise voltage. It was 9.64 microwatt RMS. You can see the plot here. It will increase, but it will not reach actually a flat or steady state value. Now we have now discussed this is the simulation at the value of the frequency, which we call the integration bandwidth. But integration bandwidth, and the rule of thumb here we have used, was 361.7 Hertz. So we actually look at the plot at this frequency, what the noise of that noise voltage was of the output, and that is 9.65 microvolts RMS, which is almost equal to that 9.64 microvolts RMS. So that's actually a very nice result. So this rule of thumb does do a very nice job in this case when you look at the simulations and also the calculations. So, okay, the next one is the signal to noise ratio. This is the plot. It starts off very large and then approaches actually some final value, which is then a steady value approximately here at 100 dBs. So the SNR was calculated using this formula. This was the output referred RMS noise voltage we have calculated. And if you now calculate this again, it will be 100.3 dBs. And I can see in the simulation it is 100.1 approximately dB. So also very close to each other. So we can see again the SNR is also in agreement with our calculations. In this example, we have seen again, in example number 10, we have seen a two-stage amplifier with a feedback capacitor, which will create a pole which will dominate actually your circuit. And since there is a capacitor, we have seen that the total output RMS noise voltage will be determined using the rule of thumb of 10 times, so 1 decade after the cutoff frequency, and that will be then our value for our total output noise voltage in RMS. Okay, that's actually for this example, considering several situations where you also have seen the input and output noise voltage spectral densities, and also the SNR in this case as a final situation. If you want, of course, increase your SNR, you need to, of course, have more noise, less noise, than your signal. Then you can consider which part of the circuit is contributing significantly to the noise at the output, and that can be, of course, reduced. For example, you can have the ratio here still as 10, so you have still a gain of 11 signal gain, by decreasing actually the value of these resistors. So you can make actually this 10 times smaller and also this 10 times smaller. You still have the gain which you require, but your resistors are smaller, but it will of course also result in more current, also more power consumption. So that is actually some optimum in it between noise and power. You can also do the same thing here and also here. So that really depends on what you really require for your application. All right, that's again for our example number 10 about the multiple stage, in this case two-stage amplifier with a RC feedback low pass filter. If you have any questions about this example or any other example, try to text me in the comment section of this video, and I will try to answer them as soon as possible. Thanks again for your attention, and don't forget to like and share this video so that we can reach more people. See you next time, and take care.